Good morning or good afternoon, at depending upon whichever time you're hearing this on. I am Neelav Bhatiya, and I had given my JEE examination in the year of 2020, wherein I had secured a rank of 1755. So, if you've been following my sessions from the previous chapters, you know I have completed a couple of them. And today we are going to take up a new chapter called Sequences and Series. Now, this chapter, from the perspective of not only your board examinations, but from the perspective of comparative examinations as well, is going to be one of the most important chapter because it has a versatile range of questions that are associated with it, right? So, having a good grasp on the concept of this chapter and how you're going to be able to solve the questions, how you're going to approach these questions. If you have a particular clarity in your mind, then it will be beneficial on two parts. It will first help you score really good marks in your board examinations, and it will also help you have a good grasp how to approach questions in your competitive examinations as well. So the first thing that as in when you approach any chapter of math, the first thing you do is kind of go through entire exercise of NCERT. And so that is how you should approach this chapter as well. And that is what we're going to do in these sessions. We are going to take up each and every exercise in NCERT about this chapter, and we are going to solve them. So before I actually start the exercises in itself, you should be aware about a couple of terms. The first term is sequences. So a sequence is like a series of numbers which have a particular relationship amongst them, right? So as you can see, a sequence is containing finite numbers, and if a sequence containing finite numbers is called a finite sequence, and if a sequence does not contain finite numbers, it is called an infinite sequence. So these are the two segregations that a sequence has, and it has terms that are arranged in a particular order. So for example, this is just an example. If I were to describe any term of a sequence in some following regard, that it is related to first term plus a constant d to the power n. So this is something random that I've written, where d is a term and a0 is a first term, and the nth term of sequence is described using this relationship. So this, when the numbers are arranged depending upon the rules that are stated here, those numbers are going to form a particular sequence, correct? And if, for example, your numbers in a sequence are arranged in an order wherein the difference between consecutive terms is always going to be the same, then that particular sequence is called an AP. AP is short for an arithmetic progression. So, for example, what would a AP constitute? So, if I say that the first term is 1, the second term is 5, and as you can see, the difference between consecutive term is 4. So, the next term in this particular AP, which is also a sequence, is going to be 9. Mind you, the rule that the term of this particular AP, in any AP, nth term of the AP could be described using this relationship, right? And how did I arrive at this? I arrived at this by knowing that the difference between consecutive term is going to be the same, which is denoted by d, is the difference between two terms, and n minus 1 is will denote the number of differences that I need to add up to reach at the nth term, correct? So just a quick trivia for you guys here is that every arithmetic progression is a sequence, correct? Because it is dependent upon this particular rule. All the terms in the AP would follow this particular rule, right? So it is also a sequence because it is following a particular rule. But every sequence is not an AP, correct? Because this particular rule, every rule of every sequence would not be able to be expressed in this form, right? So I cannot say that a sequence would constitute an AP necessarily, but I can say that an AP would always be a sequence. So these are the two things that you need to keep in mind. Moving on to another interesting part is that now we have understood if the terms have a constant difference between them, they're called an AP. What if rather than the difference between them, the ratio between the term is constant? For example, if my first term is something along the lines of 1 and my second term is 3, then my next term is 9. You can see the ratio like 9 by 3 is equal to 3 by 1 is equal to common ratio R, right? So terms that are of this form are called GP, are called part of a GP. And what is GP? GP is nothing but short for geometric progression. As we had previously discussed, every GP is a sequence because the relation of the nth term with the first term is an of a GP is equal to a r to the power n minus 1, which would imply how many common ratios the nth term is bigger by a factor of from the first term, right? So this is the relationship between GP's nth term and the first term. And as you can see, you have a concrete relationship amongst all the terms that exist in a GP. So every GP would constitute a sequence, but again, every sequence would not constitute a GP because every sequence, every common rule of the sequence would not be able to be described by such relationships, correct? So these are some of the very basic things that you need to keep in mind while any sequence has been, or any sequence, any GP, any AP has been described in this exercises. As and when more things are required to be ingrained in you all, like more rules or more equations that you need to keep in mind, I'll be sure to point that out as well. But these are some of the basic things that you need to have in mind before you approach any exercise, right? So we have discussed some of the common parts that are very useful while you're approaching exercises of this particular chapter. As we progress and solve more and more questions, there will be some more things that you need to learn, keep in mind, and I'll be sure to point them out as and when they are encountered, right? So now, without wasting any more time, let us jump to the exercise part of the chapter and kind of dwell on that, right? So the first exercise they are going to talk about today is exercise 8.1, correct? The first question the first part of the first 6 questions are described in the first line itself, which says, write the first 5 terms of each sequences in exercises 1 to 6 whose nth terms are are as follows, right? So as we had previously discussed, any sequence which describes a series of numbers would be described by a particular rule, right? So as you can see, the first 6 questions have one rule attached to them. When you plug in this rule into the numbers, you're going to get a series of numbers, and that is what is asked of us, right? So for the first question, let's just solve it, and you'll be able to get a good understanding that way. So the first question describes the nth term of the sequence as an equal to n into n plus 2. Now we are required to find the first 5 term of this particular question, right? So what I would do is I would just plug in the value of n equal to 1 up till n equal to 5, and that is how I'm going to get the first 5 terms, right? So for n equal to 1, a1 would then equate 1 plus 2, so that would be 3, correct? Now for n equals to 2, we would have a of 2 equal to 2 into 1 plus 2, that would be nothing but 2 into 3, and it's 2 here, so that will be equal to 2 into 2 plus 2, that will be equal to 2 into 4, and that is nothing but 8, correct? For n equal to 3, a of 3 would then be, plug in the value of 3 in this equation, and that is how you're going to arrive at the third term. That will be 3 into 3 plus 2, that is nothing but 5, and that is 15, correct? Similarly, for n equals to 4, you would have a of 4 equating to 4 into 4 plus 2, that is nothing but 6, and 4 into 6 is nothing but 24. For n equal to 5, you would have a of 5 equal to n, which is 5 into 5 plus 2, which is nothing but 7, and that equals 35. So the first term of the sequence is 3, then we have 8, then we have 15, then we have 24, and at the end of it all, we have 35. So 3, 8, 15, 24, and 35. These are the first 5 terms of this particular sequence. Correct? Similarly, we are going to solve it for the next question as well. For question number 2, you have the nth term described as n upon n plus 1. Correct. So this is a very simple definition for any term belonging to this particular sequence. Correct. And as I did in the first question, I try to plug in the values of n equal to 1 up till n equal to 5, and that is how I'm going to arrive at the first 5 terms of this sequence. Correct. So for a equal to 1, for a of 1, I'll plug in the value of n equal to 1 in the second part. That would give me 1 upon 1 plus 1 upon 1 plus 1, and that is nothing but 1 by 2. Similarly, for the second term, I would have n upon n plus 1, that would again be 2 upon 2 plus 1, that is nothing but 2 by 3. For the third term, I would have 3 upon 3 plus 1, and that is nothing but 3 by 4. Correct. For the fourth term, I would have nothing but 4 upon 4 plus 1, and that is nothing but 4 upon 5. For the fifth term, I would have nothing but 5 upon 5 plus 1, and that is 5 by 6. Correct. So 1 by 2, then 2 by 3, then 3 by 4, 4 by 5, and 5 by 6. These are the 5 terms that I get when I solve for the equation, when I solve for the rule an equal to n upon n plus 1. And these 5 terms will be the part of the sequence described by this rule. Correct. So again, very trivial exercise. How we are going to solve this is just by plugging the value of n into the rules, and that is how we are going to get all the terms. Right. Moving on to question number 3. Right. So the rule here is an equal to 2 to the power n, and therefore again we are going to approach it using the same logic. The first term of this particular sequence would be 2 to the power 1, and that is nothing but 2. Correct. The second term of this particular sequence would be nothing but 2 to the power 2, which is nothing but 4. Correct. I am doing nothing. I am just plugging the values of n equal to 1, n equal to 2 in this particular rule, and getting the terms like that. Right. For a of 3, I would have 2 to the power 3, and that is 8. Right. And this would be for n equals to 3, which would give me the third term of this sequence. Right. For the fourth term, I have 2 to the power 4, which would result in 16, which is the fourth term of this sequence. Right. For the fifth term, I would have 2 to the power 5, which would give me 32, which is the fifth term of this sequence. Correct. So as I solved for other exercise, I've done for this exercise as well. I've plugged in the value of n equal to 1 up till n equal to 5, and that is how I arrive at the first 5 terms of this sequence. Correct. So very trivial, very easy for you guys to understand as well as do. And you should try these exercises, because these exercises will form the base and will help you kind of not be challenged by the other exercises that are going to come ahead. Right. So you should always start at the very beginning, and no matter how you progress or how other harder questions that you might solve in this exercise, in this particular chapter, you should always start with the NCERT from the very first question. And that is my tip for you all. Start at the very beginning. Right. For question number 4, the nth term of this sequence would be described by the relationship 2n minus 3 upon 6. Correct. So we are going to solve for the first 5 terms of this particular sequence as well. Let's just write n equal to 1. So a of 1 would be 2 minus 3 upon 6. Correct. I've just plugged in the value of n equal to 1 here, and that would give me minus 1 by 6, which is the first term of my sequence. For n equals to 2, a of 2 would be 4 minus 3 upon 6. How did I arrive at 4? I plugged in the value of n equal to 2 here. So 2 into 2 is 4. 4 minus 3 equal to 1 upon 6 is 1 by 6. Correct. For n equals to 3, I have a of 3 equals to 3 into 2 is 6 minus 3 is 3 upon 6 is 6. So 3 upon 6 is nothing but 1 upon 2, and that is my third term. Correct. For the fourth term, I have 2n minus 3, so that will be 8 minus 3 upon 6, and that would equate to 5 upon 6. Correct. 8 minus 3 is 5, divided by 6 is 5 by 6. For n equals to 5, I have 2n, which is going to be 2 into 5, which is nothing but 10. So 10 minus 3 upon 6 is equal to 7 by 6. Correct. So that is how I'm going to arrive at the first 5 terms of this sequence. And yeah, that is all for the fourth question. Moving on to the fifth question. Start solving for the fifth question. For the fifth question, the rule that I have to keep in mind is an equals to minus 1 to the power n minus 1 5n plus 1. So this is the rule that I'm going to follow for this particular exercise, right? And then my first term, what would be my first term then? My first term would be nothing but minus 1 to the power 1 minus 1 5 to the power 2. Correct. How did I arrive at this? I arrived at this by plugging the value of n equals to 1 in this particular rule, and 1 minus 1 is 0. So minus 1 to the power 0. Anything raised to the power 0 is 1 itself, right? So I'll get 1 into 5 to the power 2 is nothing but 25, and hence my first term is 25. Correct. My second term would be minus 1 to the power 2 minus 1 5 to the power 3. Right. How did I arrive at this? I arrived at this by plugging the value of n, because this I need to find the value of second term. So n is equal to 2 here, right? So 2 minus 1 is 1. Minus 1 raised to the power 1 is nothing but minus 1 into 5 raised to the power 3 is 125. So the second term is minus 125. Correct. The third term would be minus 1 to the power 3 minus 1 5 to the power 4. Correct. So 3 minus 1 is equal to 2. Minus 1 raised to the power 2 is nothing but 1. So 1 into 5 raised to the power 4 would equate 625. And hence the third term of this particular sequence would be 6 to 5. Right. For a of 4, minus 1 to the power 4 minus 1 5 to the power 5. And 4 minus 1 is 3. So minus 1 raised to the power 3 would be minus 1. Correct. And 5 raised to the power 5 is nothing but 3125. So I have minus 1 into 3125. I would urge you all to calculate these things by yourself rather than looking up the solution or using a calculator. This is how you're going to solve and get these answers faster just by yourself and not by any other means, right? So I would urge you all to calculate this values by yourself without using any calculators. Yes. So the fourth term would be minus 3125. Correct. Moving on to the fifth term of this sequence, minus 1 to the power 5 minus 1. So 5 minus 1 and into 5 to the power 6. Correct. So 5 minus 1 would equate 4, and minus 1 raised to the power 4 is nothing but 1 in itself. 5 raised to the power 6 is 15625. Correct. So 1 into 15625 is nothing but 15625. Right. So that is how you're going to arrive at your answers. These are the first 5 terms of this sequence. Notice there exists a constant relationship or the constant ratio between all the terms of this GP. Minus 125 divided by 25 would equate minus 5, right? Then 625 divided by minus 125 would also equate minus 5. Then 3125 divided by 625 minus 3125 divided by 625 would also equate minus 5. So as all of these terms are always in a constant ratio, all the consecutive terms are always in a constant ratio, so this will constitute a GP. An interesting note here, even though it is mentioned that all of these are sequences, this particular rule would also be that of a GP, right? How did I arrive at this? I arrived at this by seeing that the ratios between all the consecutive terms are going to be equal, right? And this is a sequence, but this is also a special case where a particular sequence would also constitute a GP, right? So just a thing to keep in mind. Now moving on to the 6th question, right? Going on to question number 6, exercise 8.1, correct? So for the 6th question, the rule that has been described is A of n equals to n into n square plus 5 upon 4, right? So this is particular rule, but it is nothing but arithmetic calculations for you all from now on. Like you just have to plug in the value of n here, and that is how you're going to arrive at the solution. So for n equals to 1, the first term would be 1 into 1 square plus 5. So that will be 1 into 1 square is just 1 plus 5 upon 4. So 5 plus 1 is equal to 6. 6 upon 4 is equal to 3 upon 2. And that is your first term, right? For n equals to 2, the second term would be 2 into, so 2 square is going to be 4 plus 5 by 4, and cancel this out like this. The term that you get is 9 upon 2, correct? Moving on to the third term. A of 3 would be equal to 3 into 3 square is 9. 9 plus 5 upon 2. So this is going to be 14. You cancel this out. 7 remains. I'm sorry. This cancel 4 out, not 2. You got 4 here, not 2. So 3 into 7 is 21. And in the divisor, you have 2 left. So that will be 21 upon 2. Correct. These are very trivial calculations. You just need to plug in the value of n equal to 1, 2, 3, 4, and 5. And that is how you're going to arrive at the answer, right? For n equals to 4, A of 4 would be 4 into, so 4 square is nothing but 16 plus 5, correct? We have 4 in the denominator as well. 4 and 4 gets cancelled. 16 plus 5 is nothing but 21, correct? For the fifth term, we have A of 5 equals 5 into, so 5 square is 25 plus 5 divided by 4, correct? So let me just rub some of the part here and I'll be able to better solve it. So what should I rub? Rub this, right? You can rub the rule. We know the rule, right? So A of 5 would then equate 5 into 5 square is nothing but 25 plus 5, which is as mentioned in the rule, upon 4. So this is 30, right? 25 plus 5 is 30 and this is 4. Cancel this out. This becomes 15. This becomes 2. 15 into 5 is nothing but 75. and in the divisor we have 2, so that will be 75 by 2. So 3 by 2, 9 by 2, 23 by 2, 9 by 2, 21 by 2, 21 and 75 by 2. These are the first 5 terms of your sequence. Correct. Now we have solved the first 6 questions which are of the same type, and yeah, so that is going to be the first 6 questions of this particular exercise. Moving on to the remaining questions. Let's see what they tell us to do. Correct. So for the next questions, which are in the range of question number 7 to question number 10, we need to find the indicated terms in each of the sequences in exercise 7 to 10 whose nth terms are. So we have been given a particular rule, and based upon that rule, we need to calculate the term that is associated with that particular sequence. Right? We are given the rule, we are given the term number that we need to find, and that is how this question is stipulated. That is what this question stipulates. Right? So for the question number 7, we have a of n described by the relation 4n minus 3, and we need to find a of 17 comma a of 17 comma a of 24. Correct. So the relation is described by a of n equal to 4n minus 3. We need to find a of 17 and a of 24. So a of 17 would be nothing but me plugging in the value of 17 in this rule. So that is 4 into 17 minus 3. 4 into 17 is nothing but 68 minus 3, and that would be 65. Similarly, for the 24th term, I have 4 into n is equal to 24, because it has been stipulated that we need to find the 24th term. 4 into 24 is nothing but 96 minus 3 is equal to 93. Right? That is how you're going to find the 17th term and the 24th term respectively. Right? So that is the 7th question for you guys. Moving on to the next question, question number 8. We have a of n described by the relation n square upon 2 to the power n, and we need to find the value of a of 7. Right? So this is also not going to be very difficult. It's fairly trivial for you guys to solve. Just for a of 7, you need to plug in the value of 7 into this rule right here. Right? So 7 square is nothing but 49 upon 2 to the power 7. 2 to the power 7 is nothing but 128. Right? So I have, this should be written a bit better. 2 to the power 7. So I have 49 upon 128, and that will form my 7th term of this particular sequence. Correct? Moving on to the 8th question, or maybe, to the 9th question. In question number 9, the rule is given to us as minus 1 to the power n minus 1 n cube, and we need to find the value of a of 9, which is the 9th term of this sequence. Right? So 9th term of this sequence would entail minus 1 raised to the power n minus 1. Yes, so we have 9 minus 1, and then we have n cube. Right? So n cube, which is 9 cube, it's going to be written like this. Right? So n minus 9 minus 1 is 8. Minus 1 to the power 8 is going to be 1. Even power negative term is always going to be positive. Keep this thing in mind. So this is going to be just 1. And 9 cube is going to be 729. So 1 into 729 is 729. So this is your 9th term of this sequence. Correct? So that was all from the 9th question. Moving on to the 10th question, we have A of n described by the relation n into n minus 2 upon n plus 3, and this would describe the nth term of this sequence. So we need to find the 20th term of this particular sequence, right? So A of 20, which will describe the 20th term, would be 20 into 20 minus 2 upon 20 plus 3. Correct. So 20 into 18 upon 23. 20 into 18 is going to be nothing but 360 upon 23. Correct. So that is your 20th term of this sequence. And so that was question from question number 1, question number 7 to question number 10. And let us now proceed to the next questions of this exercise. Let's start with that. So for the next questions, we have write the first 5 terms of each of the sequences in exercises 11 to 13 and obtain the corresponding series. Right. Okay. So this has been fairly straightforward. So for question number 11, we have been given A of 1 equals to 3 and A of n equals to 3 A of, wait a minute, 3 A of n minus 1 plus 2, right? So why we have been given the first term separately from the rule is that every subsequent term in this particular sequence would be derived from its previous term, right? So therefore we need to be given a first term in this sequence, because A of 1 cannot be derived from any other term because that would represent the first term, right? So that is why the first term has been given separately to us and we are required to find the first 5 terms, right? So without wasting any more time, let's do it. So for the first term, we have A1 equal to 3. This has already been given to us. We need to find the next 4 terms, right? So A of 2 would equate 3 into 3 because that would signify the first term, right? Plus 2, right? So A of n minus 1 would be A of 1. So let me just make it very clear for you all, so there's no confusion right here. So A of 2 would be described by 3 into A of 2 minus 1 plus 2, right? So 3 into A of 1 is nothing but 3 plus 2, that would be 11, right? That is your second term. Moving on to the third term, you have third term described by 3 into A 3 minus 1 plus 2, so that is nothing but 3 into A of 2 is nothing but 11 plus 2, so that is 33 plus 2, that is nothing but 35, correct? A of 4 is nothing but 3 into A of 3 plus 2, which is nothing but 3 into 35 plus 2. 3 into 35, 105. 105 plus 2 is equal to 107, and that is your fourth term. For the final term, we have 3 into A of 4 plus 2, 107. So that is 3 into 107 plus 2. 107 into 3 is 321, and 321 plus 2 is nothing but 323. I'm going to write this up here as well. So I had 3 into 107 plus 2. So 3 into 107 is 321 plus 2, and that is nothing but 323, right? So this is the fifth term right here and right here for you guys to see. So we have 11. So we have 3, starting from 3, we have 3, 11, 35, 107 and 323 as the first 5 term of this sequence, correct? Moving on to the 12th question, right? To the 12th question. In the 12th question, we have A of 1 equals to minus 1, and we need to find a of n equating to a of n minus 1 upon n for n greater than equals to 2. Now, as we discussed in the previous question as well, what is the requirement for us being given the first term separately and the rule separately is that every term in the sequence is dependent upon its previous term. But because the first term cannot be derived from the previous term because it represents the first term, so we have been given the first term separately. That is the main reason why. So the second term would then be a of 2 would then be a of 2 minus 1 upon 2, correct? And that is nothing but minus 1 upon 2, correct? Similarly, the third term would be a of 3 minus 1 upon 3, and that is that will be a of 2, so minus 1 by 2 upon 3, that is minus 1 upon 6, correct? The fourth term would be a of 4 minus 1 upon 4, that is nothing but minus 1 upon 6 by 4, and that is nothing but minus 1 by 24, correct? Moving on to I need to find the fifth term as well. I'll write the fifth term here. A of 5 is nothing but a of 4 upon n, that is nothing but 5. So a of 4, we have already derived a of 4 as minus 1 upon 24 divided by 5, and that is equal to minus 1 upon 20, correct? That is your fifth term. So these are the first 5 terms of this particular sequence. I have minus 1, I have minus 1 by 2, I have minus 1 by 6 and minus 1 by 24, and I have minus 1 upon 20, correct? These are the first 5 terms. Moving on to question number 13th, I believe we have remaining. So in 13th question, we have a of 1 equals to 2, a of 1 equals to, a of 1 equals to a of 2 equals to 2. And the relationship that has been described is a of n equals to a of n minus 1 minus 1, right? So why have we been given the second term separately? That is because the expectation of us was that the first 2 terms in this particular sequence are going to be 2, right? Then every term is going to be dependent upon the previous term, right? So this is a particular sequence where the rules are described as such. The first 2 terms are constant, and then we have to follow the rules. So a sequence could have that as well. Sequence could have selective rules being applied on certain portions of the term. You could separate out rules as and when you require, but as long as it follows a certain rule, it is fine, right? So we have the first term as 2. We have the second term is equal to 2 as well. For the third term, we have a of 3 minus 1 minus 1. That will be a of 2 minus 1, and that is nothing but 1. Correct? Because a of 2 was 2, so 2 minus 1 is 1. For a of 4, I have a of 3 minus 1. 4 minus 1 minus 1. So I have a of 3, which is equal to 1 minus 1, and that is nothing but 0. Right. For a of 5, I have a of 4 minus 1. So a of 4 is nothing but 0. 0 minus 1 is minus 1. Correct. So I have 2, 2, 1, 0 and minus 1 as the series. Right. So that was the 13th question as well, right? The 14th question is going to be an interesting one because we have been described with a Fibonacci series, and depending upon that series, we need to kind of derive other terms as well, right? So the Fibonacci sequence is described in this particular question as a of 1 equals to a of 2 equals to 1, and for every other term, for n greater than 2, for every other term is described by a of n minus 1 plus a of n minus 2. Correct. We need to find the value of a of n plus 1 upon a of n for n equals to 1, 2, 3, 4, and 5. Right. So this is what we are required to do. We have to find out the values of these terms for described by this particular relationship. Right. So for doing that, I need to know the value of Fibonacci sequences starting from a of 1 up until a of 6, right? Because the fifth term would be described by a of 6 upon a of 5, and that is the last term that I need. So before starting the actual question, let me just find out all the values of the Fibonacci sequence up until a of 6, and then I'm going to plug in these values into this particular equation, and that is how I'm going to arrive at the solution, right? So without wasting any more time, moving on, I have a of 1 described by a of 1 described by the value 1. A of 2 is also been said as 1. A of 3 would be a of 3 minus 1 plus a of 3 minus 2, and that is nothing but a of 1 plus a of 2, and that is equal to 2. Correct. A of 4 would subsequently be a of 3 plus a of 2, plugging in the value of the relation a of n equals a of n minus 1 plus a of n minus 2. Correct. I'm doing nothing but I'm using this relation here. So a of 3 has already been told to us as 2 plus 1. So that would be 3. Right. A of 5 would be a of 4 plus a of 3. So a of 4 is 3 plus 2, that is 5. Correct. A of 6 would be a of 5 plus a of 4, and that is nothing but 5 plus 3, and that is 8. So the first 5 terms that I have, or the first 6 terms of Fibonacci sequence would be 1, 1, 2, 3, 5, and 8. Let me write all of these terms somewhere, and then I'm going to use these values when I'm calculating a of n plus 1 upon a of n, right? So let me just erase this part maybe, and I'm going to write all of these terms here. So a of 1 equals to 1, a of 2 equals to 2, a of 3 equals to 2, a of 4 equals to 3, a of 5 equals to 5, a of 6 equals to 8. Correct. So I have written all of the terms of the Fibonacci sequence here, and I'm going to rub all of this off, and I'm going to find out a of n plus 1 upon a of n, right? The rule that I have to follow while finding out the first 5 terms is a of n plus 1 upon n, right? So this is the rule that I'm following. So for n equals to 1, I have a of 1 plus 1 upon a of 1. That will be a of 2 upon 1. A of 2 is nothing but 1, and a of 1 is also 1. So 1 upon 1, and that is 1, right? For n equals to 2, I have a of 3 upon a of 2. Correct. A of 3 is nothing but 2 upon 1 is nothing but 2. Correct. For n equals to 3, I have a of 4 upon a of 3. A of 4 is nothing but 5. And a of 3 is nothing but 3. And I'm sorry, may goof it up a bit here. A of 4 for n equals to 3, a of 4 is nothing but 3. And a of 3 is nothing but 2. Correct. So I have 3 by 2 as the third term, right? For n equals to 4, I have a of 5 divided by a of 4, and that is nothing but a of 5 would be 5 divided by 3 would be 5 by 3. Correct. For a of find out the value of value because of this rule. For n equals to 5, I have a of 6 upon a of 5. A of 6 is nothing but 8 upon 5 is 8 by 5. Correct. So that is my sequence. So described by this particular sequence, I have the terms as 1, 2, 3 by 2, 5 by 3, and then 8 by 5. Correct. That is how the terms in this particular sequence are described by. So without wasting any more time, we will kind of jump to exercise 2, and we'll try to see some part of exercise 2 as well. We will see some 3-4 questions before wrapping up the session and continuing in on the next session. But as we have some time left, we can maybe see a couple of questions from the next exercise as well, right? So that is, so the next exercise, would involve certain use of these terms as well, right? So you would also have to know what an arithmetic mean and a geometric mean would be. So an arithmetic mean would be described by the summation of two terms divided by 2, and the geometric mean would be described by the root of their multiplication, right? So these are the sum of very basic things that you need to keep in mind, but don't mind this as well. As in when we are going to solve these questions, I will be sure to point these things out to you as well, right? So without wasting any more time, we can start with the next exercise as well, right? So in the next exercise, the first question that has been asked of us is that find the 20th term and the nth term of the GP, which is described by the following sequence, right? So I have a GP which is of the form, I have 5 by 2, I have 5 by 4, I have 5 by 8 right here, right? And so on and so forth. If you find out the ratio between these two terms or the ratio between these two terms, you would arrive at the constant ratio, right? So what I'm going to do is R is equal to A of 2 upon A of 1, right? That would be nothing but 5 by 4 upon 5 by 2. 5 and 5 gets cancelled. I have 2 by 4 as my ratio, which is nothing but half, right? So the common ratio that I have right now is half. For a GP, any term in the GP can be described by the relation A of n equals A r to the power n minus 1. Correct. So the 20th term in this particular GP is going to be A of 20. It's described by A r to the power n minus 1. And plugging in the value of n equals to 20 in this relation, the first term that you have is 5 by 2. And the common ratio that you have is 1 by 2. So 20 to the power 20 minus 1. So the 28th term of the GP is 5 2 to the power 20. Correct. That is the 20th term of your GP. Right. The nth term of this particular GP would be, I'll write that as well. So the nth term of this particular GP would be A r to the power n minus 1. Correct. So A here is 5 by 2. R is 1 by 2 raised to the power n minus 1. Right. So I would have 5 into 2 into 2 to the power n minus 1. You can add these powers up. N minus 1 plus 1 is just n. So 5 2 to the power n would describe any term in this GP. Right. So that is the nth term. And we also found out the 20th term of the GP. Yeah. So that was the first question for you guys. Moving on. Question number 2. You have find the 12th term of the GP whose 8th term is 192 and the common ratio is 2. Correct. So we need to find out the 12th term of the GP whose 8th term is 192. So let me just write this. A of 8 has been given to us as 192. R, which is the common ratio, has been given to us as 2. We need to find A of 12 and what it equates. Correct. So in any GP, as you know, a GP's term could be described by the relation A of n equals A r to the power n minus 1. Correct. So yeah, there you have it. A of 8 would be A into r to the power 8 minus 1. We know the common ratio. The common ratio has already been given to us as 2. 192 right here into, we don't know what is A, right? So A would be as it is. And in the RHS, I would have 2 to the power 7. Correct. So A would be nothing but 192 upon 2 to the power 7. So 2 to the power 7 is nothing but A to the power is nothing but 192 and 2 to the power 7 is nothing but 128. And when you do the calculation, you can cancel this out by 64. That would be 2. That would be 3. And so the first term of the GP would be 3 upon 2. Now that you have the first term of the GP figured out, you'll be able to calculate the 12th term as well, right? So how you're going to do that? Let's just, going to calculate the 12th term as well. So A of 12 would be A into r to the power 12 minus 1. Sorry, 21 I have written. 12 minus 1. Correct. So I have A as 3 by 2 into r to the power 12 minus 1. So r has been given to us as 11. 2. So I'll just write 2 to the power 11. And this 2 and this 2 gets cancelled. I have 2 to the power 10 remaining here. 3 into 2 to the power 10. 2 to the power 10 is nothing but 1024. And when you do the calculations for yourself, the final answer that you're going to arrive at is 3072. So that is the 12th term of your GP. Correct. Moving on to the third question. So this is going to be the last question we solve for the day. In the coming session, we are going to solve more questions in this exercise, and we'll solve all the remaining questions of this exercise in the next session. Correct. So for question number 3, you have the 5th term of the GP described to you as P. You have the 8th term of the GP given to you as Q. You have the 11th term given to you as S. Right? You need to show that Q square is equal to P into S. Correct. How we are going to do that? We're going to assume a very general GP, right? With the first term as A, common ratio as R, and the relationship describing each of the term as A of n equals A into R to the power n minus 1, right? So then, so you need to show that. So before starting the question, I would like to find out what P, Q, and S are actually, right? So P is the fifth term. So P would be A of 5, and that would be nothing but, if described by this particular relationship, it would be A R to the power 4. Correct? Can you understand that? Because the first term is A and R is the common ratio that we have assumed. So the Pth term would be A 4 to R to the power 4. Correct? The Qth term would be A of 8, and that would be nothing but A R to the power 7. Correct? Very simple to understand, very trivial. The S term would be A of 11. I mean A of 12. I'm sorry. It has been given to us as it has been given to us as A of 11. Correct? That would be nothing but A R to the power 10. Correct? So we have the Pth term described as, we have the P is equal to A R to the power 4 as the fifth term. We have Q as A R to the power A into R to the power 7 as the 8th term. S as equal to A into R to the power 10 as the 11th term. We have these three terms in our description. And moving on, so we are going to first evaluate the LHS, then we'll evaluate the RHS, and when both of these are equal, we'll be able to conclusively show that Q square equal to PS, right? So I'm going to write LHS here and RHS here, right? So what is Q square? Q square is nothing but A R to the power 7 whole squared. Correct? How do I arrive at this? I have already denoted Q as being equal to A R to the power 7. Correct? So I'm just squaring up this entire term. So doing that, I have A square here and 7, the powers get multiplied right here. So 7 into 2 would be 14. So I would have R to the power 14. A square R to the power 14 would be my LHS. Let us solve RHS. RHS is nothing but P into S. P into S is nothing but A R to the power 4 into A R to the power 10. Right? When you multiply these terms, you would add the powers up. So that would give you A1 plus 1 into R4 plus 10. Right? The powers have gotten added up. I multiplied A and R and R. And what I finally get is A square R to the power 14. And when you compare these two terms, A square R to the power 14 and A square R to the power 14, you know that the LHS and the RHS are equal, and hence we have conclusively showed that Q square equal to PS. Right? So this has been question number 3 of this particular exercise, and we were able to finish about 17 odd questions today from the first exercise and some part of the second exercise as well. Moving on, we will solve all the remaining questions of the second exercise and the last exercise of this chapter as well. Meanwhile, I would urge you guys to familiarize yourself with all the terms and all the formulas that are given to you in the NCERT. So before the next session, I would like you all to be familiar with what is an AM, what is a GM, and how you would be able to find these two things, right? So just have a quick look at how you're going to solve questions by using the formula that are given to you in the book itself, and doing that would be sufficient knowledge for you guys to be involved in and reactively solve the questions in the second exercise, right? So that is a very small tip from my side. Yeah, so this has been all, and we'll continue in the next session.